Welcome to this walkthrough of LeetCode problem number 1021, remove outermost parentheses. In this session, we'll break down the problem, explore its requirements, and discuss an efficient approach to solve it. Let's dive in. In this problem, we're working with valid parentheses strings, which are sequences of open and close parentheses that follow specific rules. A valid string can either be empty, represented as an empty string, or it can be formed by concatenating two valid strings together. For example, if A and B are valid strings, then AB is also valid. Another way to form a valid string is by enclosing a valid string within a pair of parentheses, like A. Now, an outermost parentheses string is one that doesn't contain any other valid parentheses strings as its proper substrings. For instance, in the string, the outermost parentheses are the ones at the very beginning and end, the first and the last. Our goal is to take a valid parentheses string S, remove the outermost parentheses from every primitive substring within S, and return the resulting string. A primitive substring is essentially a part of the string that cannot be split further into smaller valid strings. Let's look at some examples to understand the problem better. In the first example, the input string S is. This string can be divided into two primitive substrings, and for each of these substrings, we remove the outermost parentheses. From removing the first and the last gives us. Similarly, from removing the outermost parentheses also gives us. When we concatenate these results, we get the final output string, which is our answer. In the next example, the input string S is. This time, the string can be divided into three primitive substrings, and for the first substring, removing the outermost parentheses leaves us with. For the second substring, removing the outermost parentheses again gives us. Finally, for the third substring, removing the outermost parentheses leaves us with. When we concatenate these results, we get the output string, which is the answer. This example shows how the process works when there are multiple primitive substrings with varying levels of nesting. Now, let's consider the third example where the input string is simply. Here, the string consists of two primitive substrings, and for each of these substrings, removing the outermost parentheses leaves us with an empty string. Concatenating these empty strings results in an output of an empty string. Finally, let's review the constraints and edge cases. The string S will always have a length between 1 and 100,000, and every character in S will either be an opening or closing parenthesis. Importantly, S is guaranteed to be a valid parentheses string. Some edge cases include strings with only one pair of parentheses, deeply nested structures, or strings composed of multiple primitive substrings. These examples and constraints help clarify the range of inputs we'll handle in this problem. To tackle LeetCode problem number 1021, our goal is to process a valid parentheses string and remove the outermost parentheses from each primitive substring. A primitive substring is a valid parentheses segment that cannot be broken down further into smaller valid substrings. First, the brute force approach involves splitting the string into primitives as they are detected, removing the outermost characters from each primitive, and then concatenating the results. This is done by using a counter to track the depth of parentheses, resetting the counter when a complete primitive is found. We considered a few approaches to solve this. While this approach is straightforward and operates in O(n) time complexity, it introduces some inefficiencies due to redundant substring operations and requires O(n) extra space. Alternatively, we explored an optimized single-pass approach that processes the string while tracking the depth of parentheses. Instead of explicitly splitting substrings, we can ignore outermost parentheses by only appending characters to the result when the depth is greater than 1. This method is highly efficient, operating in O(n) time with O(1) space, as it avoids additional memory usage for substrings. The optimized single-pass approach is not only efficient but also avoids the extra space overhead of substring storage. Another option we considered was a stack-based approach, which simulates the matching of parentheses. In this method, we push opening parentheses onto the stack and pop for closing parentheses, tracking the depth based on the stack size. Characters are appended to the result only when the stack size is greater than 1, indicating that we are inside a primitive substring. This approach, while conceptually clear, requires O(n) space for the stack, making it less space efficient compared to the single-pass method. Ultimately, we chose the optimized single-pass approach due to several key observations. First, depth tracking alone is sufficient to detect outermost parentheses without the need for explicit substring operations. By appending characters directly when the depth is greater than 1, we eliminate unnecessary overhead. This realization that depth alone serves as a reliable indicator for outermost parentheses was the pivotal insight that made this approach both elegant and efficient. The chosen strategy is not only efficient but also straightforward, minimizing the likelihood of edge cases in the implementation. Let's take a look at how this approach translates into code. We initialize an empty list to store the result and a variable to track the depth of parentheses. As we iterate through the string, we check each character. For an opening parenthesis, we increment the depth, and if the depth is greater than 0, we append the character to the result. For a closing parenthesis, we first decrement the depth, and again append the character to the result if the depth remains greater than 0. At the end of the loop, we join the result list into a single string and return it. This implementation is concise, processes the string in a single pass, and avoids the need for extra data structures beyond the result list. By directly leveraging the depth counter, we achieve a clean and efficient solution that handles all valid parentheses strings correctly. When comparing the approaches, the brute force method, while simple to grasp, is less efficient due to the overhead of substring operations. The stack-based method provides a clear conceptual framework but consumes additional space for the stack, which can be avoided. The optimized single-pass approach, on the other hand, strikes the perfect balance between efficiency and simplicity. It processes the string in O(n) time with just O(1) extra space, making it the most practical choice for this problem. By avoiding redundant operations and unnecessary space usage, this method not only delivers optimal performance but also ensures the implementation remains clean and easy to understand. Choosing this approach allows us to solve the problem effectively without compromising clarity or maintainability. To solve this problem, we need to process a valid parentheses string and remove the outermost parentheses from every primitive substring. A primitive is a valid substring that cannot be broken down further into smaller valid parts. For instance, in the input string, we identify two primitives, and removing the outermost parentheses from each gives us the final output. To achieve this, the algorithm follows a structured approach. First, we initialize some variables. We use either a stack or a counter to track the nesting depth of parentheses. For simplicity and space efficiency, we'll use a counter called depth. We'll also create an empty string result that will store the output. Initially, the depth is set to 0, and we are ready to process the string one character at a time. By analyzing each character, we can determine whether it contributes to the primitive or not, and adjust the result accordingly. Now let's break down how we handle each character during the iteration. When we encounter an opening parenthesis, we increment the depth by 1. This indicates that we are moving one level deeper into the nesting. However, we only append the character to the result if the depth is greater than 1. This ensures that the outermost opening parenthesis of the primitive is skipped. For closing parentheses, the depth is decrement by 1, signaling that we are exiting a level of nesting. Similarly, we only append the character to the result if the depth is greater than 0. This allows us to skip the outermost closing parenthesis. By applying these rules consistently, we ensure that only the inner parentheses within each primitive are added to the result string. Finally, after processing all characters in the string, we return the result string, which contains the modified input with the outermost parentheses removed from every primitive substring. There are a few key insights that make this algorithm both effective and efficient. First, the depth variable serves as a simple and intuitive way to track the nesting levels of parentheses. By appending characters only when depth 1 or depth 0, we effectively exclude the outermost parentheses from the result. Second, the algorithm naturally identifies and processes primitive substrings by incrementing and decrementing the depth counter. When the depth returns to 0, it signals the end of a primitive, and the process seamlessly continues for the next one. This sequential processing eliminates the need for additional data structures or segmentation logic. Finally, this method is highly efficient. It scans the input string in a single pass, resulting in an O(n) time complexity, where n is the length of the string. Additionally, by using a simple counter instead of a stack, the algorithm achieves O1 space complexity, making it both elegant and practical for large inputs. Let's illustrate the algorithm with an example to solidify our understanding. Consider the input string. We begin by initializing depth to 0 and result to an empty string. For the first character, the depth becomes 1, so we skip appending it since it's the outermost parenthesis. The second character is another, increasing the depth to 2. Now, since the depth is greater than 1, we append it to the result, which becomes. The next character is, reducing the depth to 1. Since the depth is greater than 0, we append it, making the result. Another follows, increasing the depth back to 2, and we append it, resulting in. The next character is, reducing the depth to 1, and we append it, making the result. Finally, A reduces the depth to 0, so we skip it. The same logic applies to the second primitive substring, ultimately yielding the output. This walkthrough highlights how the algorithm processes each character methodically to construct the result. This algorithm is not only simple but also optimized for efficiency. It performs all operations in a single pass over the input, ensuring an O(n) time complexity. By using a counter instead of a stack, we maintain a constant space complexity of O(1), which is ideal for handling large inputs. Additionally, the algorithm is robust enough to handle various edge cases. For an empty string, it simply returns an empty result. For a single primitive, such as, it removes the outer parentheses and returns an empty string. Nested primitives, like, are handled seamlessly by removing only the outermost pair, resulting in. These optimizations and considerations make the approach both effective and reliable for all valid parentheses strings, ensuring correctness and efficiency in every scenario. This Python implementation solves LeetCode problem number 1021, remove outermost parentheses, using a simple and efficient algorithm. The function takes a valid parentheses string s and removes the outermost parentheses from each primitive substring. We start by initializing an empty list result to collect the characters that will make up the final result. Additionally, we use a variable balance to track the nesting level of parentheses. This variable is increment for every opening parenthesis, and decrement for every closing parenthesis. The algorithm processes each character in the input string s one by one. When encountering an opening parenthesis, it checks if the current balance is greater than 0. If true, it means the parenthesis is not part of the outermost pair, so it gets added to the result list. Regardless, the balance is increment. Similarly, when encountering a closing parenthesis, the balance is decrement first. If the resulting balance is still greater than 0, the parenthesis is not part of the outermost pair and is added to the result list. By the end of the loop, the result list contains only the inner parentheses without the outermost ones. The list is then converted back to a string using join and returned as the output. This approach ensures we process the input in a single pass, making the algorithm efficient with a time complexity of O(n), where n is the length of the string s. The space complexity is also O(n), due to the use of the result list to store the output. This implementation handles all valid input cases, including nested and consecutive primitives, while maintaining correctness. This is the Java implementation of the LeetCode problem remove outermost parentheses, problem number 1021. The logic mirrors the Python implementation, using a string builder for efficient string manipulation and a balance variable to track the depth of parentheses. The key difference lies in Java's type declarations and the use of enhanced for loops for iterating through the character array. This approach ensures O(n) time complexity, where n is the length of the input string. We begin with the input string. To solve the problem, we initialize an empty list called result to store the characters that will be part of the final output. Additionally, we start with a balance variable set to 0, which will help us track the depth of nested parentheses. Now, examining the first character, which is, we increment the balance to 1. Since this is the first parenthesis and it represents the outermost layer, we do not add it to the result. Moving to the second character, which is also, we increment the balance again, making it 2. Since the balance is greater than 1, this indicates that the parenthesis is part of an inner layer, so we append it to the result. At this point, the result contains Next, we process the third character, which is a closing parenthesis. We decrement the balance to 1, and because the balance is still greater than 0, this parenthesis is part of the inner layer and should be added to result. Now, result becomes, comma. The fourth character is another closing parenthesis. Decreasing the balance to 0 tells us that this parenthesis closes the outermost layer, so we do not append it to the result. Moving on to the fifth character, which is, we increment the balance to 1. Since the balance is 1, this parenthesis is part of the outermost layer, so we skip it and do not add it to the result. However, the sixth character is another, which increases the balance to 2. Since the balance is now greater than 1, we append this parenthesis to result, making it, comma. Continuing, the seventh character is a closing parenthesis. We decrement the balance to 1, indicating that this parenthesis belongs to an inner layer. Therefore, we append it to the result, which now becomes, comma, comma. The eighth and final character is another closing parenthesis. Decreasing the balance to 0 shows that this parenthesis is part of the outermost layer, so we do not add it to result. At the end of this process, we join the characters in result to form the final output string. Now, let's consider a second example with the input string. As before, we initialize an empty result list and set the balance to 0. Looking at the first character, we increment the balance to 1. Since this is the outermost parenthesis, we do not append it to result. For the second character, another, we increase the balance to 2. Since the balance is greater than 1, this parenthesis is part of an inner layer, so we append it to result. At this point, result contains. The third character is a closing parenthesis. Decreasing the balance to 1 indicates that this parenthesis is part of the inner layer, so we append it to result. Now, the result becomes, comma. The fourth character is an opening parenthesis, which increases the balance to 2. Since balance is greater than 1, we append this parenthesis to result, making it, comma. The fifth character is another, which increases the balance to 3. This indicates a deeper level of nesting, so we append this parenthesis to result as well. At this stage, result becomes, comma. The sixth character is a closing parenthesis. Decreasing the balance to 2 confirms that this parenthesis belongs to an inner layer, so we append it to result, which now becomes, comma, comma. Next, we process the seventh character, which is another closing parenthesis. Decreasing the balance to 1 shows that this parenthesis is still part of the inner layer, so we append it to result. At this point, result becomes, comma, comma. Finally, the eighth character is a closing parenthesis. Decrementing the balance to 0 tells us that this parenthesis closes the outermost layer, so we do not append it to result. After processing all the characters, joining the elements of result gives the final output string. In the third example, the input string is. Again, we start with an empty result list and a balance of 0. The first character is. When we increment the balance to 1, we recognize that this parenthesis is part of the outermost layer, so we do not append it to result. The second character is a closing parenthesis. Decreasing the balance back to 0 confirms that this parenthesis also belongs to the outermost layer, so we skip it as well. The third character is another. Once more, increasing the balance to 1 indicates that this parenthesis is part of the outermost layer, so we do not add it to result. The fourth and final character is a closing parenthesis. Decreasing the balance back to 0 shows that this parenthesis closes the outermost layer, so we do not append it to result. After processing all characters, the result list remains empty. Joining its elements results in an empty string as the final output. To summarize, this algorithm effectively removes the outermost parentheses by using a balance tracker to determine when a parenthesis is part of the outer layer. Only parentheses contributing to a balance greater than 0 are added to the result, ensuring that the outermost layer is excluded from the final output. The time complexity of the solution is O(n), where n is the length of the input string. This is because the algorithm processes each character of the string exactly once in a single pass. During the traversal, operations like comparisons, updates to the balance variable, and appending characters to the result list all take constant time for each character. After the traversal, the join operation combines the characters from the result list into a single string. The time required to join a list of k characters is proportional to k, and since the result list contains fewer than n characters, this operation also takes O(n) time. Adding these together, the total time complexity becomes O(n) plus O(n), which simplifies to O(n). The space complexity of the solution is O(n). This is mainly due to the result list, which stores the characters that are not part of the outermost parentheses. In the worst-case scenario, such as with deeply nested parentheses, nearly all characters in the input string could be added to this list, making its size proportional to the length of the input. The balance variable, which tracks the depth of the parentheses, is a single integer and uses constant space, O(1). Similarly, the join operation creates a new string from the result list, and its space usage is directly proportional to the size of the list, adding up to O(n). Therefore, the total space complexity is determined by the result list and the join string, both of which are bounded by O(n). When we combine these factors, the overall space complexity remains O(n). Now let's analyze the best, average, and worst-case scenarios. In the best case, where the input string is empty, the algorithm does not perform any iterations, and both time and space complexity reduce to O(1). In the average case, the algorithm processes each character in a typical input string exactly once, leading to O(n) time and O(n) space complexity. For the worst case, with deeply nested parentheses, nearly all characters could end up in the result list, but even then, the time and space complexity stay at O(n). This consistency in performance makes the solution robust across all cases. Comparing this to a naive approach highlights the efficiency of the given solution. In a less optimal method, one might repeatedly slice the string or split it into multiple substrings to remove the outermost parentheses, which could lead to O(n)² time complexity due to the repeated operations on the string. By contrast, the provided solution processes the string in a single pass, achieving O(n) time complexity. This is a significant improvement, especially for larger inputs. Mathematically, the time complexity can be validated by noting that the algorithm performs n iterations of the loop, where each iteration consists of constant time operations such as comparisons and updates. The final join operation takes linear time relative to the size of the result list, which is at most n. Adding these together confirms the total time complexity is O(n). For the space complexity, the proof lies in the memory usage of the algorithm. The result list, which holds at most n characters, is the primary contributor to the space complexity. Additionally, the balance variable uses constant space, O(1), and the join string requires space proportional to the size of the result list. Summing these factors